Hello everybody, this is a video on the sampling theorem. Now, just as a quick review, to sample a continuous signal, we can multiply it by an impulse train with sampling frequency f of s. Then, to reconstruct the signal, we multiply it by an interpolation function, which in some sense connects the dots, making it a digital to analog, right? So we go from continuous, then we sample it, making it discrete, and then to make it analog again, we use this interpolation function, which we will discuss at the very end of this sampling theorem analysis. Now, let's start to think about some of the conditions in terms of the sampling frequency. Let's try to check kind of our intuition here. Let's see if we can agree on the following facts. If our sampling frequency approaches infinity, or we have an infinite sampling frequency, then our reconstruction should be approaching perfect, right? I'm going to go back to some of the previous notes here, but we can see that if we have some smooth curve like this shown in this figure, then we multiply it by this impulse train, we get something like this. And you can imagine the resolution as the sampling frequency becomes very large, or in other words, the spacing between these samples becomes smaller and smaller and smaller. You can imagine that the resolution is going to just get better, right? So as we increase this f of s, this sampling frequency, it should approach a perfect reconstruction. And then we can kind of imagine on the other side that if we take the sampling frequency down to something super, super low, the reconstruction is going to be worse and worse and worse. And we can think about this in a similar way. Imagine that we have this diagram here, but now our sampling frequency is very low, or the spacing between these samples is very large. Then what we're going to have is this kind of blocky, inaccurate representation of our signal. So these are kind of like the edge cases, right? But obviously we're gonna want to get a more nuanced idea of what this sampling frequency should be to kind of get a perfect reconstruction. But just intuitively, we should be able to see that like the sampling frequency is a very important parameter to analyze when we're talking about reconstruction. And this is a figure just to kind of confirm what we talked about, right? So we have this original arbitrary signal, x of t. That's just some sinusoidal signal. And then we have the second figure below it is this very low sampling rate signal. So the gray curve underlaid is the same original signal as x of t. And you can see we're just sampling at these 2 points. And obviously, like, this is not giving us a good representation at all of what the signal is. And the one below is a little bit better, right? We have more points, right? We have double the frequency, yet it still is a really poor representation of the signal. And then the figure on the bottom is this oversampled regime, or this high sampling rate, where we can see that we have a lot of points and it's able to get a pretty accurate recreation of our original signal. So let's talk about how like this nuanced frequency is, right? Let's talk about it. One other way of looking at this from another point of view is from the point of view of interpolation. These are two curves that have different kind of interpolations. So what you're looking at here is the gray curve is the original signal, we'll say. And remember that this interpolation function is kind of just doing the best it can to connect the dots. So we can look at these blue dots as being samples that we took from the gray curve. You can see that they all lie on that gray curve. And then the blue, interconnecting it, is the interpolation function, turning it from a discrete to an analog signal. So it's kind of doing its best to connect the dots. And as you can see, it's not perfect, but it does a pretty good job. It's pretty smooth and it follows the lines pretty closely. So that would be an example of pretty good interpolation. Now, look at the signal right below it. As you can see, this signal seems to have a much higher frequency, or at the very least, high frequency components. So when we take samples of it, they all lie on the curve, but as you can see, the interpolation function has no chance of predicting that behavior, right? From the first to the second curve, you can see it's trying to do a similar shape as the blue figure, but it has these high oscillating terms, which means it doesn't have a really good chance of recreating the signal. One way that we could look at this is that we just need way, way, way more points. The points need to be much closer together. So a lower sampling period or a higher frequency, a higher sampling frequency would be necessary to reconstruct such a signal. So let's kind of like put together these point of views and let's start thinking about the analysis. So theoretically, we can reconstruct any signal with an infinite sampling frequency. But obviously, this is not useful. This is not feasible, right? So let's just make some kind of predictions of times where we wouldn't get perfect reconstruction. In the block diagram, the reconstruction is performed by multiplying the signal by the interpolation function, as we talked about. The function draws smooth curves interconnecting these discrete points. So this red figure that we talked about here, we can see an example of the poor interpolation. And we talked about it as the error coming from these high frequency components. So we can kind of use that idea to make a prediction about what constraints there will be to reconstruct a signal perfectly. So a reasonable prediction that we can make is a signal with higher frequency than the sampling frequency is prone to poor interpolation or imperfect reconstruction. Or said another way, the more useful way, is we can say signals whose frequency is lower or kind of in the same order of magnitude as the sampling frequency has a better chance of being reconstructed. We haven't done any math here. This is just a qualitative analysis so far. But this is a pretty reasonable assumption based on these two figures that we looked at, right? So that's where we're going to start our quantitative analysis. We're going to start the analysis under the assumption that the frequency spectrum of our original signal x of t, which has the Fourier transform x of f, is band limited. So what that means is that after some point plus or minus b, we have 0 high frequency components. So we're just going to call them, whenever I refer to high frequency components, all I mean is frequency components outside of this plus or minus b, right? So stated formally, you can say x of f is equal to 0 for some b such that the absolute value of f is less than or equal to b, right? So don't let the shape of this bother you. This is just some arbitrary Fourier transform, and it's band limited. So it's contained between minus b and plus b. So now let's kind of put some math to this. All we're going to do, if you haven't watched the previous video on sampling, I go more into depth into the math of how we sample. All we're going to do is we're going to look at this process from the perspective of the frequency domain, and that will reveal a lot of really important facts to us. So if this feels a little bit out of left field, go watch that video first and then come back. So previously we expressed the sampled version of our continuous time signal x of t as this xp of t. That was given by the product of the time domain signal with the impulse train I of t, with sampling period t of s. So this is kind of what we previously talked about. But now let's look at the Fourier transform of x of p of t, right? So the Fourier transform of this can be found by the convolution of the Fourier transforms of the signal and impulse train in the frequency domain. So because we're multiplying these two signals in the time domain, that corresponds to frequency domain convolution, right? So we're just going to call the Fourier transform of the original signal x of f, and then we need to find the Fourier transform of the impulse train. And I don't show it here, but it can be shown that it is equal to like delta of f minus m over ts with a factor of 1 over ts. And that can be shown with a Fourier series and then with the definition of the Fourier transform. And rewritten in probably the easiest way is that 1 over ts is simply equal to the sampling frequency. And then that convolution, remember that convolution with deltas is just that original function. But notice that each of the delta terms is shifted by the index of the summation. So ultimately, what do we get? This final term, f of s summation from m equals negative infinity to infinity of x, which is the shape x, that big x is the shape of the original signal's Fourier transform. And then we have this f minus mfs, where m is the index of the summation. So all that this really is you have a bunch of copies of the original spectrum of the original signal all across the Fourier transform, going off from negative infinity to positive infinity. So this can be a little bit confusing at first, and I'm now realizing that showing this weird shape was maybe a little bit confusing. But pretend that this was a triangle, right? This is the triangle from negative b to b. And you can imagine that this triangle here is the original copy of the original signal, and it's centered at 0. And then every next copy is simply just being shifted by f of s, right? So this copy on the right is centered at plus f of s, the next one is at plus 2f of s, and the same thing on the negative side. And what I'm showing here is what the spectrum looks like for different sampling frequencies, right? So I'm gonna read what I wrote here. The Fourier transform of the impulse train is a scaled impulse train with spacing of fs in the frequency domain. If we considered x of f to be an arbitrary band-limited spectrum, then the result of the convolution gives us copies of this spectrum spaced out in intervals of f of s. So this is just what it looks like. And we're going to come back to this picture because this is really what the sampling theorem comes down to. But just to kind of complete our reconstruction, let's talk about what we do next. After this convolution, what do we do? Then, we're not interested in all these copies, right? We're interested in x of f because that's what's going to give us our original signal. So what we're going to do is we're going to pass this spectrum through a low-pass filter that has the following specifications. If the frequency is less than or equal to half of the sampling frequency plus or minus, then we're going to scale that part of the spectrum by t of s. So let's just slow down and see why we're scaling it by t of s. Notice that when we were talking about the convolution, we had this scaling factor of t of s. So basically that gain of our filter is simply just to cancel out this term and ensure that when it passes through our filter, the amplitude is just 1. And then this second part, if f is less than or equal to f of s over 2, all we're doing is I'm defining the range of that original signal, this original copy with the gray dotted lines. I'm rewriting that in terms of the sampling frequency, because we can easily say that that's minus b to b, but you'll notice that if you look at the next copy, it's at f of s. So if you cut that value in half, you can see that it goes from minus f of s over 2 to plus f of s over 2. So that's going to be the way that we're going to define our low-pass filter. And if it's still a little bit confusing, hopefully these drawings clarify the picture. The filter is 0 everywhere except in the original copy, constantly reminding ourselves that this is the Fourier transform of the original signal, which is what we're ultimately trying to extract. Cool. So now let's talk about the grand finale. What are we trying to do all this? Why are we even talking about this? We're trying to understand the conditions for where we get perfect reconstruction. So let's talk about that. Now that we understand that our filter is picking out the original copy in the spectrum, we can ask, what must be true about the frequency spectrum of x of p of t such that when we pass it through our low-pass filter, we get exactly x of f, the spectrum of our original signal? From the picture, it is clear that for the bottom figure, the sampling frequency is very large. And we can see that these copies are very far apart from each other. So when we send it through our low-pass filter with that shape, we can pick out the original signal x of f very easily, right? The second one, and this is probably the most important part, notice that because f of s is smaller, right? It's smaller, therefore the copies are closer together. There is what we call overlap in the frequency components, or the more proper term is aliasing, right? So the part that's bad about this is that the way I've shown it is I've shown them overlapping just to demonstrate that they really are overlapping in the spectrum. But what's going to happen is that these signals are getting added together. So you're not going to really see this overlap, but you're going to kind of see this flat line. So we're going to get like a triangle, and then where they overlap, they're going to cancel each other out, and we're going to get this kind of flat line. And that is not going to give us the same x of f, right? It's going to give us a kind of similar shape, but with some flat lines. But the point is that it's not the exact same triangle. So as we say here, when we pass this through the filter of x of f, we're not going to get x of t. And the top figure is where we can draw our conclusion. This shows the minimum condition for no aliasing. And we can state it as follows. For the sampling theorem, to sample and reconstruct a sample perfectly such that x of t, the original signal, is equal to x of r of t, the reconstructed signal, the sampling frequency needs to be greater than or equal to twice the band limiting frequency. So what do I mean by that? This condition is just basically observed from looking at this plot. In order for these copies to not overlap, your frequency needs to be scaling it, or sorry, not scaling, but shifting it. Because remember that f of s, your sampling frequency, is what determines the spacing between these copies, right? Looking at this equation here, this is the equation for the copies in the spectrum. So when you change f of s, you're changing how spaced apart they are. And it matches our theory, right? Like this is an example of when f of s is large, and in this case it's equal to 4 times the band limiting signal, and you can see that like easily we get perfect reconstruction. There's not even close to overlapping. And it matches the theory that we made earlier, where if f of s goes to infinity, these copies are going to be nowhere near each other. And this is a case where kind of like it's going towards 0, right? The frequency is too low. They're overlapping. Therefore, we're not going to get that perfect reconstruction. So this is the condition for perfect reconstruction. And we made this with the assumption that our sample was, or sorry, our frequency spectrum was band limited. And if it wasn't band limited, it should be pretty obvious as to why it would not even be possible to sample such a thing. Because if it wasn't band limited, this b would be infinity, and there's no way that we can produce a sampling frequency that big. So this is the important part, and b is sometimes called the Nyquist frequency. It's essentially just the magnitude of the largest frequency component of some signal. And that's what the sampling theorem says. One last note, going back to the interpolation function, we saw that it was a sinc function in the time domain. And you'll notice the shape of our low-pass filter that we're using to pick out the original copy in the spectrum is a pulse function. And the Fourier transform of a pulse function in the time domain is a sinc function. And by duality, we can say that a time domain function for a pulse in the spectrum is a sinc function, right? So we can use that duality property to say that if we have a pulse in the frequency domain, then the time domain signal that corresponds to that, the inverse Fourier transform, must be a sinc function. And this is really why we have the sinc function. Nobody kind of said, oh, like, we're going to interpolate, let's use a sinc function. It came more from just the math of creating this low-pass filter in the frequency domain that is isolating a chunk of the spectrum that we want to pick out. So that is all in the sampling theorem.